Hi, so today I'm going to solve for you two problems from Chapter 6 of our textbook. So the first problem is, find the area of the region bounded by the parabolas x squared equals 4py and y squared equals 4px. And we know that p is a positive constant. So the first thing I'm going to want to do is I'm going to simplify these equations to y equals. I feel like that makes it easier to graph and easier to solve. So the first equation, x squared equals 4py squared equals 4py, and that's the same as y equals x squared divided by 4p. And now the second equation is y squared equals 4px, and that is the same as, well, y equals the square root of 4px. So from here, basically, first thing I'm going to do, make it easier, is sketch the graph. So I'm going to draw a graph right here. Now, when I sketch this graph, I'm going to know that I'm going to say p equals 1. Say p equals 1. So that means it's going to be x squared of x squared divided by 4p. Actually, I'm going to say yeah, we can use that. P equals 1. So x squared divided by 4, and y equals the square root of 4px. So x squared. So say you plug in 1, that's going to be 1/4. Then 2 is 1. And 3 is going to be 9/4, which is 2.5. So essentially, the curve is going to look something like that. Now, the second equation, y equals square root of 4px, so it's going to be square root of 4 times x. So to make it easier, I'm just going to plot points where this equals an actual number. So I know it equals a number when x equals 1. So that's going to be, when x equals 1, it's going to be y equals the square root of 4, which equals 2. And another one I know is when x equals 4, that means it's going to be the y equals square root of 16, which is 4. So I'm going to do 4 and then 4. So that's going to make our curve look like this, something like that. So the region we want to find is this one right here. And so we know that this intersection is actually going to be 4p, 4p. That's what we have here, 4p. And this intersection here is going to be 0, 0. So we know that 4p, so the intersection is 4p, 4p, and 0, 0. So a good way to test this is to actually plug in these points here and see if they match. So 4p, we already said that p equals 1. So this is essentially 4, 4. So we plug in 4 for this equation. First equation is going to be y equals 4 squared over 4, which is equal to 16/4, which is equal to 4. So 4, that works. So for this case, x equals 4, so y equals 4. So then we plug in the second equation, y equals square root of 4 times 4. And so that's essentially the same thing as saying square root of 16, which is 4. So these two curves do intersect at 4p, and 0, 0. I'm going to check this again. You can choose p as a different number. So let's say p is 2. So we're going to have y equals, and we're still going to use 4p as an example. So we're still going to have 8 squared over 8 equal, which is saying 64/8, which is 8. And y equals the square root of 8 times 8, which is the same as saying square root of 64. So I'm still thinking of the previous one. So it's square root of 64, which is 8. So that's the work again. So as you see, it's if you matter what you put in for p, and it's always going to, the intersection point's always going to be 4p, 4p. So we know that. So now we're talking about the area. So we know that we found out the area is really the area underneath the top curve minus the area underneath the bottom curve. Right? So in this case, the top curve is y equals square root of 4px. And the bottom curve from this range is going to be the x squared equals 4py equation, which is y equals x squared over 4p. So the area is the area underneath the top curve minus area underneath the bottom curve. So to do this, we're going to do an integral. So we're going to do the integral from 0 to 4p, since that's our range 0 to 4p, 0 to 4p. We're going to do the integral from 0 to 4p of the area. So the area underneath the top graph is going to be this integral from 0 to 4p of the square root of 4px, right? And so we're going to, and that's the top curve. So we minus the bottom curve, and the bottom curve is going to, so it's going to be x squared over 4p. So dx. So here's our integral to find out the volume. So make it so simple, we can write these two different, we can split this up. So first thing I'm going to do, I'm going to split it up into the integral of from 0 to 4p of the square root of 4px dx minus the integral from 0 to 4p of x squared 4p dx. Now, I'll simplify it again to make it easier to see. I'm going to write this in a different way. I'm going to convert these formulas into a different form to make it easier to see. So, this right here is going to be the integral of 0 to 4p of 4px to the 1/2. That's the same as saying to the square root. Dx minus the integral of from 0 to 4p. It's saying 1 over 4p times x squared dx. So here, this we're going to use different derivative rules that we used before, the power rules. So we know that the antiderivative of x to the 1/2 is 2/3 x to the 3/2, right? So, we take that, and the antiderivative of x squared is 1 over 3 x cubed. So now we're just going to plug 4px as x in for this equation, for the 2/3, and as x for the 2/3 times x to the 3/2. And we're going to plug, we're just going to put 1 times 4p as part of the coefficient for for the 1/3 times x cubed. So this integral, so basically the antiderivative from 0 to 4p is going to be 2/3 times 4px to the 3/2 minus 1/3 times 1 over 4p x squared from 0 to 4p. So there's our antiderivative. And now we can simplify this into 2/3 4p x halves minus 1 over 12p x squared from 4p to 0. So actually what I did when I anti-derived it, I basically joined these two integrals together again. So from 0 to 4p. So now what I'm going to do is I'm going to plug in 4p and 0. It's going to be a long one right over here. So we have 2/3 of 4p times 4p 3/2, right, minus 2/3 4p times 0. Actually, here's our range right here to the 3/2. Right, minus 1 over 12p 4p squared minus 1/12p 0 squared. Now this, as you know, 0 squared is 0 times something is 0. So this is going to cancel out to 0. And this one right here is going to cancel out to 0. So we are left with 2/3. I'm gonna multiply. So it's going to be 16p squared instead of 4p times 4p. To the 3/2 minus 1/12p 4p squared. So, I can actually simplify this even more to 2/3 16p squared to the 3/2 minus, so we know that 4p squared is 4p times 4p, which is going to be 16p squared. So we're going to have 16p squared over 12p. Now I can cancel out this p squared and p. So I'm going to be left with 2/3 16p squared 3/2 minus 16p over 12, which can even be simplified even more to 2/3 16p squared to the 3/2 minus 4/3 p. And so basically the area of this region is going to depend on what p is. So the final volume equation is 2/3 16 times p squared to the 3/2 minus 4/3 p. So, and that is that's going to be the area of the region bounded by the parabolas x squared equals 4py and y squared equals 4px. Okay, so the second problem is sketch the region bounded by the curves below and find the volume of the solid generated by revolving this region about the x-axis. So my starting equations are y equals x cubed, x plus y equals 10, and y equals 1. So I'm going to do the same thing I did in the previous problem and convert this all to y equals. So really the only one I have to do that with is this x plus y equals 10. And so that's going to be y equals 10 minus x. So again, I'm also first thing, since the equation first thing question asks us to sketch the region bounded by these curves. So to sketch this region, I'm going to draw a grid right here. So the easiest equation to start off with is y equals 1. So that's just going to be this line right here as y equals 1. It's going to be this straight line right there. Now, next one is y equals 10 minus x. So say, next I have to expand these a little bit more. So, we know that when x equals 0, y equals 10. And then when x equals 10, y equals 0. So this equation, this line is just going to be the straight line right here. Let me expand that. So now, the last equation we do is y equals x cubed. And that's just a simple, this shape right here. Let me get that right. So that's what that's going to be like. So we have, this equation is y equals 10 minus x. This is y equals 1. And this one, I'll write it down here, is y equals x cubed. So now the region we want to find is this one right here. So, when we're finding the volume of the solid generated revolving around the region, the equation is a bit more complicated than this equation right here, than the integral of the top equation minus the bottom equation. When you're finding the volume of a region after revolving around the x-axis, it's actually going to be y equals the integral from a to b. This is going to be your region. Right, of pi times whatever your function is. Let's say f of x is my function squared dx. So that's using the washer method to find the volume. So in this equation, as you see, this shape is kind of hard to do using one equation. So I'm going to split this up into two separate intervals. So I know that from two different intervals. In one interval, y equals x cubed is the top function, and in another integral, y equals 10 minus x is the top equation. And so they meet at supposedly y equals 2. So right here. And so this starts out, it's actually from pre-calculation, that these y equals 1 and y equals x cubed, they intersect at 1, 1. And these intersect at 2, 8. And this one, these intersect again also at 9, 1. These are here. So these are my endpoints. So my two intervals are going to be from 1 to 2 and from 2 to 9. So these are my two. So now I'm going to doing this. I'm going to still use this equation, but now I'm going to have my volume equals 2 of these equations. So, and it's still the top equation minus the bottom equation, just like it was in the other one. So here's my integrals. My integral is going to be for the first interval is going to be the integral from 1 to 2 of x cubed. Sorry about that. Get that wrong. X cubed minus 1, since y equals 1. And this is going to be squared. And so since pi is a constant in this equation, you could actually take it out of the integral and just multiply it times the integral. So I'm going to write pi times the integral of 1 to 2 of x cubed minus 1 squared dx. And this is going to be the volumes of this first interval rotated around the x-axis. Now for the second one, since this is a total volume, I'm going to do plus, as I said before, multiply the pi times the integral. So the integral from 2 to 9 of 10 minus x, it's in parentheses, minus 1 dx squared. So here, this is my written out integral. So basically, first thing I'm going to do is I'm actually going to integrate. I'm actually going to solve this. I'm going to do x cubed minus 1 times x cubed minus 1 and 10 minus x minus 1 times 10 minus x. So first I'm going to want to simplify this equation. So this is the same thing as saying the pi times the integral from 2 to 9 of 9 minus x d of x squared. So I'm going to want to solve this out. So it's going to end up being pi times the integral from 1 to 2 of x to the 6th minus 2x cubed plus 1 dx plus pi the integral from 2 to 9 of 99, actually 99, it's not 99, I'm going to do 81 actually, 81 minus 18x plus x squared dx. So now that I have this equation, I'm going to integrate using the power rule. So I'm going to be pi times, we're just in parentheses because the pi goes to the whole. It's actually pi times. No, I don't have to write it in parentheses because it goes to not to each element. It goes to actually the whole equation. So it's going to be 1, pi times 1/7 x to the 7th minus 1/2 x to the 4th plus x from 1 to 2 plus pi times 81x minus 9x squared plus 1/3 x cubed from 2 to 9. So now I'm going to want to do as I did in the first problem and plug in my two limits. So it's going to be pi times 1/7 times 2 to the 7th minus 1/2 2 to the 4th plus 2 minus pi times 1/7 times 1 to the 7th minus 1/2 1 to the 4th plus 1 plus over here pi times 81 times 9 minus 9 times 9 squared plus 1/3 9 cubed minus 81 times 2 minus 9 times 2 squared plus 1/3 2 cubed. And you see this is a very long equation right here. I'm trying to get the whole thing. Here's our equation. So the first part of the equation is going to equal 26.030 minus, and the second part of the equation right here is going to be 2.020, and then this will be plus, for this equation, it's going to be 243 minus, for this part of the equation, it's going to be 128.667. So the first is going to be 26.030 minus 2.02 plus 243 minus 128.667. And that is going to equal 138.343. And that's going to, this number right here is going to be the volume of this original region revolved around the x-axis. Thanks for watching. I hope you learned a lot.